incorporating energy, wavelength, and electron transitions. An electron in a hydrogen atom goes from the energy level of n is equal to 8 to n is equal to 1. Calculate the energy of the photon given off. So key here is that it's photon. So first, we know that we can find the energy of an electron transition through the following equation. Delta E is, I'm going to write the little E sign because that's my electron transition energy, is equal to negative 2.18 times 10 to the negative 18 joules times 1 over the final energy level squared times 1 over the initial energy level squared. And then you just plug all of your numbers in. When you plug that in, that gives you that the energy change for the electronic transition is negative 2.15 times 10 to the negative 18 joules. However, you want energy of photon. So, remember that in the law of conservation of energy, the energy is only transferred, so the energy of the electron must equal the inverse of the energy of the photon. So since 1 is negative, your energy of your photon is therefore equal to 2.15 times 10 to the power of negative 18 joules. Now it says calculate the frequency of this photon and its wavelength in nanometers. Is this photon in the visible, ultraviolet, or infrared region of the electromagnetic spectrum? Okay, so you are looking for frequency and wavelength. I know that energy is equal to Planck's constant times frequency, and energy is equal to high C over wavelength. Planck's constant times speed of light divided by the wavelength. So you have to use here the energy of the photon because you care about the wavelength of the photon and its frequency. Doesn't matter which one you solve first. I'm going to first solve for frequency. So frequency will have to be energy over Planck's constant, which will be, I'm going to erase this for a second, my energy of 2.15 times 10 to the negative 18 joules divided by Planck's constant, which equals 3.24 times 10 to the 15 inverse second. That's my frequency. Now my wavelength, I will solve for taking Planck's constant and speed of light dividing by the energy. So 6.626 times 10 to the negative 34 joule seconds times the speed of light divided by my energy, 2.15 times 10 to the negative 18 joules. Then my wavelength is 9.245 times 10 to the power of negative 8 meters. Since I want nanometers, I then use my nanometer conversion. And my wavelength will equal 925 nanometers. Now I want to know, is this in the visible, ultraviolet, or infrared region? Well, I know that visible is 400 to 700 nanometers. And this is pretty much the highest that it goes, so this is a visible light. Calculate the energy in kilojoules per moles of these photons. So the energy that you have is 2.15 times 10 to the negative 18 joules. That's the energy of the photon. So you write the energy per one photon. And you want this in kilojoules per mole. So one thing that you could do is, I know I want kilojoules, so I'm just going to convert. And, well, I need to get rid of photon, but I want mole. So the conversion that we know and that we can always use is Avogadro's number, 6.022 times 10 to the 23rd particles over 1 mole. In our case, these particles are photons, so then you would just multiply it by Avogadro's number. And the answer will come out to be 1,290. I did 3 significant figures to be consistent, and then that's